Hello everyone and welcome to this last session in the NPTEL course Machine Learning for Core Engineering Disciplines. We have come a long way together in this course and I am happy that you are still watching the videos for this course and hopefully you will learn something new today. So in today's tutorial we will continue what we started out with in the previous tutorial, right? After finishing our discussion of the vanilla neural networks which we had applied to the Boston pricing data set, we had gone on to look at recurrent neural networks or RNNs, and in particular we said that we will apply RNNs to predict the formation energy, right? So the energy of formation of nanopores in graphene, right? A nanopore is a tiny hole which is formed by removing certain atoms from the graphene lattice, and every nanopore has a particular shape. What I told you in the previous video was that every nanopore can be mapped to a unique string representation which we call strong, the string representation of nanopore geometry, and now the problem reduces to how we can map this canonical strong, right, to the formation energy, right? And for this we will use recurrent neural networks because this is sequential data. Here the features, the order of the features has an importance, right? It's not like other vanilla neural networks where the features can enter the model in any order. Okay, so to start with, of course, as always we import the libraries that are required in the tutorial, and these include in this particular case tokenizer, right? So we have since these are text, right, these are characters, these have to be tokenized and converted into vectors, so we import the tokenizer. Then we import from Keras preprocessing.sequence pad sequences. This is an important command especially when dealing with text, because your string representations can have different lengths. Maybe you have a strong with 20 characters, maybe you have a strong with 30 characters, maybe you have a strong with 50 characters, but at the end of the day when they go into the neural network model they should all have the same length, otherwise the model will get confused, right? So we need to pad the sequences with certain padding so that they all have the same length, right? And these other things that we are importing like the sequential layers and so on you saw earlier, but here we are also, apart from the dense layers, importing the simple RNN, LSTM, GRU layers and so on and so forth. We of course also import the train test split from sklearn.model selection, and from sklearn.metrics we get the mean absolute error, mean squared error, R2 score, R squared score and so on. Okay, so like I said we are using a data set of string representations of nanopore geometry, strong sequences and the corresponding formation energies which can be used for regression tasks in material science of nanoporous materials, and the data set is from a paper that our group published last year in the Journal of the American Chemical Society, and the features is essentially the canonical strong, right, the string sequences representing the nanopore structures in graphene, and the target variable like I said is just the formation energy which is reported here in kilocalorie per mole. So right, so if you wanted to form a mole of these pores, what's the value? Of course you can convert that to a per pore formation energy as well. Okay, so here we are assuming that you will be able to access the GitHub page for our group, and there is a strong repository, string representation of nanopore geometry repository, from where you can directly download this data set. Of course if you download it on the computer you can directly read it from the CSV file as well. Alright, so once that is done, this is how we can read the data. You already know that we typically use a fixed random state, right, and this is how you can get the train test split. So the features are the canonical strongs and the target variables are the formation energies, and the shape of the data set is as follows. There are 20,812 data points, right, and 5, I mean this is the there are actually 4 target variables that we have. In this particular tutorial we are only dealing with one target variable, right, which is the formation energy, but if you looked at the source we have also looked at other target variables which we will not be discussing today. right. So now to pre-process, we have to do a few other things than what we did earlier. Earlier we were doing a standard scaler when we were just looking at numerical features. Here, because we are looking at text, we have to tokenize the characters and then we have to pad it to make sure that each of these strongs is of the same length, right. So neural networks cannot work directly with raw strings, and therefore we convert the canonical strong sequences into numerical form, right. So the first step is tokenization, where each unique character is assigned an integer ID, right. So one could say, for example, A, B, C can be 1, 2, 3. In our case we have armchair, zigzag, fully bonded, corner and singly bonded, right, A, Z, F, C, S. So each of these can be assigned an integer ID, right. So that's tokenization. And then there is padding, right. All sequences are padded to the same length, which can be the maximum length of a particular strong in your data, the maximum length of any strong in your data set, and this will enable consistency across all the strings, right. And shorter sequences can be padded with 0. So this ensures all samples have consistent dimensions when fed into the recurrent neural network. Okay. So now you see that we have tokenized the data, right, and then we are using this fit on text on the training data set, and then the texts will be converted to sequences, right. So this is done for both the train and the test data, right. And finally we are finding out the maximum length in the data set and then padding, post padding, right. So padding at the end, so you can either do pre or post padding. In this case we have done post padding, and we are now defining the vocabulary size, which is the length of the word index, right. So here we have 5 different types of characters, A, Z, F, C, S, and then +1. You often also want to have the padding character here, right. So we are adding +1. Okay. So this is finally what we get, right. The vocabulary size is 6 and the maximum length is 48. Okay. So now we are going to try various model architectures, right, and for this we are going to use a simple RNN, we are going to use a long short term memory as well as a gated recurrent unit, and by now you already know that each model will have an embedding layer which converts the tokens into vectors. At the end of the day, machine learning model works with vectors or tensors. So in this case what we are doing is these are getting converted to vectors. Okay. So we will have to convert the tokens into vectors, and then you can have the recurrent layers, whether it's an RNN, LSTM, GRU, or combinations of ANNs with these to process the sequential dependencies. And as a regularization strategy we will explore the use of dropout, and finally you can get the regression output from your dense layers if needed. Okay. So we are importing TensorFlow here, and then the sequential module, and then embedding simple RNN, LSTM, GRU and dense layers, and here we are setting some of the hyperparameters. To obtain the best performance you will have to tune the hyperparameters. So this is telling you a number of the RNN units, the dropout rate, the number of the fully connected layer size, right, the embedding dimension, the number of epochs, batch size, and so on and so forth. Okay. So here we are building the recurrent neural network RNN model, right, and this is where you have to add the embedding. We already discussed that you have to embed the characters here, and you can see that we are employing the tanh activation function with the simple RNN recurrent neural network, and we can also try an LSTM model or a GRU model. So by using these if else statements we have just made a wrapper function which, if passed the appropriate argument, will make one of these model architectures. So that's what is happening here, right. So this is one of the 3 models, and yeah, obviously if you don't specify it to be one of these 3 there is an exception or an error that's thrown out. Okay. So now here we are adding the dropout rate here, and then for the fully connected layers we are adding the activation function, and for optimizer we are again using adaptive moment estimation or ADAM. We are tracking the mean squared error loss, and we are also tracking the mean absolute error. Okay. We already discussed the concept of early stopping in the lectures as well as in the previous tutorial. Here we are using a patience parameter of 10, which means we will wait up to 10 epochs for improvement in the validation loss. Okay. And restore best Bates true, right. If that doesn't happen, you go back to the best Bates, right, if the model loss has deteriorated. Okay. And again these are some of the other parameters that we are defining here. Alright, so let us go ahead. We will now train the simple RNN, LSTM and GRU models using these hyperparameters, and we have discussed these kind of concepts: early stopping, which is stop training if validation loss does not improve, and reduce LR on plateau, which is reduce the learning rate when the progress stalls. So when you reach a plateau in the improvement of the loss function, that means you can try with a lower learning rate. So that is one of the features that was enabled here, right. We were reducing the learning rate by half if there was no reduction in the loss function within 5 epochs. Alright, so this is where we are now training the models. We are just looping over the 3 types of models that we were interested in: a simple RNN, an LSTM and a GRU, and again we are using 10% of the training data as the validation set. Yeah, we want the number of epochs was already specified previously, right. We had included all the data here, 50 epochs, batch size 32 and so on. So those are the things which are being specified here. Callbacks, we want verbose, we want output, a lot of output to be given by the Python code. Alright, so once you run this code, you will see that all the different types of models, there is a for loop, so all of the models will be trained, and then it is going to tell you, right, for every epoch, right, out of the 50 epochs what is happening, what is the learning rate that is being employed, what is the MSE loss, what is the MAE loss, and so on and so forth. Okay. So I have deleted some of these pages here for brevity, but like I said, the original notebook is available online on the GitHub repository for our group, and you can go and access them from there. So let us go ahead and evaluate the models, right. So now that we have trained multiple sequence models like a simple RNN, an LSTM and a GRU, and we also trained a hybrid GRU ANN, and you will see that this particular model is the one that does the best, right. So sometimes your RNNs, right, such as GRU, LSTM, they process the sequential inputs and make them ready, and later you may have to pass them through dense networks to introduce more nonlinearities to be able to predict the target variable. So in this case you will see that this is actually the strategy that worked the best, the hybrid GRU plus ANN. So we will now evaluate them on the test set using the mean absolute error, root mean squared error, and the coefficient of determination or the goodness of fit R squared. Okay. So here, yeah, we are just evaluating all the metrics. We are predicting the model, we are predicting the target variable based on the trained model, and then we are calculating the mean absolute error, the root mean squared error, and the R squared score. Alright, and we, like earlier, we are looping through all the 3 types of models: simple RNN, LSTM and GRU. So let us see how these models are faring. The R square model, and if you see here that this is on the whole data set, is actually quite bad for the GRU and the simple RNN. It is reasonable for the LSTM, right. So and this MAE, I want to remind you, is in units of kilocalorie per mole. So the 74 is actually quite a large number. This 10 is somewhat reasonable. It's not bad, but it's not that low either, right. Root mean squared error is about 16. Later you will see that through the hybrid GRU plus ANN model, we are able to bring this down from 16 to about 8. So that is the best performing model. But in this case, our take home message is that the simple RNN is not working, the GRUs, which does not capture the long range dependencies in the input, is also not that good, whereas the long short term memory LSTM is reasonable, right. It has an R square of 0.97 and a mean absolute error of 10.9 kilocal per mole, right. So the final model obviously will require hyperparameter tuning. So you will have to experiment with different architectures and optimizing hyperparameters, either using k-fold cross validation or using just a simple validation set. By the way, the code for this is available on our GitHub repository corresponding to our last year's 2024 paper on where we introduced this Strong's concept. We will now build a final sequential model. And what are the key choices here? Obviously we have to specify the dimensions of the vectors here. So we are using 16 dimensional vectors, so that's the embedding layer. Then the GRU layers, how many GRU layers there are, and then like I said, you can also have deep dense layers which progressively reduce the dimensions, enabling the model to learn nonlinear relationships. And finally, because we are interested in one regression output, this is not a multi-class classification output, we just have a single neuron with no activation. And we are using the mean squared error as the loss function. We are using the ADAM optimizer for obtaining the adaptive learning rate, and then we are using MAE as an additional metric that will be monitored during the training process. Now for more details on the architecture, why this was chosen, how were the hyperparameters tuned, you can visit the GitHub page on the canonical Strongs, right. So this you can click and you can access this particular link. So for now we will go ahead and proceed with our tutorial. Okay. So what we are going to do here is we are making a hybrid model, right, which combines GRU plus artificial neural networks, and here we are defining the input dimensions and the output dimensions and so on, and this is the artificial neural network stack, right. So once we have deployed the GRU, right, from there we are using dense layers coming down from 40, 32 nodes, 24 and finally down to 1 node, right. And again we are using the ADAM optimizer with a MAE metric, and also the loss function is MSE. These parameters remain the same as earlier. The validation split is 10%, we are using 50 epochs and a batch size of 32, and we are using the verbose mode for output. Okay. And this is allowing you to evaluate the hybrid model here using the test data, right, test X, the padded Strongs and the test Y. Okay, so this again is the code that is going on. You can notice immediately that the MAE has come down drastically, right. It is only about 6 kilocalorie per mole compared to, if you looked at the best performing model here, it was about 10 kilocalorie per mole. So it has come down, it has almost halved, right. And I am not showing all the epochs here, but if you download the Jupyter notebook you will be able to find it. Okay. So let us now compare all the models. These metrics you already saw earlier, and look at this new model here, hybrid GRU plus ANN, excellent R square 0.99, RMSE of about 8.76 and an MAE of only about 5 kilocal per mole. So this is on the whole data set, so that is very nice here. Okay. And finally we can plot the loss curves. So this is what we are doing here. We are doing it for all the models, the simple RNN, the LSTM, right. So we are plotting the both the training loss as well as the validation loss on a log scale. So the X label reads epochs and the Y label reads loss. So let us see how this looks. Okay, so this is a plot of the loss function. You can see here that the losses are coming as follows. So in this case what you are seeing is that the validation loss is lower than the training loss, which can be surprising, but I will outline a few reasons for why that is happening. So that is for the simple RNN. For the LSTM, which was actually the best performing out of the 3 simpler models, you can see again that the train loss and the validation loss are coming down. In this case look at the scale here, this is 10 to the 4 here for the validation loss, this is 10 to the 3. So you can already make out from the scale of the loss versus epoch plot as to which model is doing well. And then for GRU the scale again here is 10 to the 4, so this we know is worse than the LSTM, and it is about the same as the simple RNN model. In fact, if you remember the table, you actually saw the same thing pan out in the R squared value. So the R squared value of the simple RNN and the GRU are very similar to each other, and this is what you can see here as well, right. So the loss is plateauing around 10 to the 4, whereas for the LSTM it is coming around 10 to the 3. And finally, this is the loss curve for the hybrid GRU plus ANN model. This is really nice because here you see that the loss has come down to further only 100, right, and this model is very nice. It is a very generalizable model because unlike in the previous cases, what you see is the train and the validation losses, they are roughly the same number. So that means that the model is working well, there is no under fitting, there is no overfitting, so this is good. Now I want to outline a few reasons as to why the validation loss can be lower in these three cases, right, in the previous set of loss versus epochs plot, and this could be due to either regularization. We have used dropout and regularization, which will increase the training loss, but the validation loss is measured without it. So that could be one reason. The validation set could be a simpler data set, so that can produce a lower loss. You can have batch variation, so some training batches may be harder, which inflates the average training loss. So the way to deal with this validation set characteristics is to use cross validation rather than a fixed validation set. Of course that will increase the cost, so it is a compromise that you will have to work with. And there can also be some learning dynamics involved. There are temporary phases where the validation improves faster than training, which is what you may be seeing in some of these plots here. Okay, so we are almost near the end of this particular tutorial. So we finally are looking at the parity plots here, right. So we are plotting a scatter plot, right, with both the with the actual values of the formation energy on the x axis and on the y axis or the vertical axis the predicted values. Okay, so here you can see the parity plots. Yeah, the code I just went through quickly because this kind of a code by now you have written many times. Okay, so like the metrics revealed, the simple RNN is not able to capture the formation energy at all, right. You are almost predicting a constant value, right. This is a really poor model, and for the GRU a similar thing is happening. So the simple GRU and the simple RNN, they are not at all able to capture the sort of a structure that is involved in the string representation of the nanopore geometry. The LSTM is working well in the intermediate formation energies, but for very high formation energies it is not able to predict, right. So it is predicting a value of 1400, whereas sorry, it is predicting a value of 1200, whereas the value should be 1400. So it is under predicting, and for very low formation energies it is actually over predicting, right. You can see here that the predicted value is 600, whereas the actual value is only 400. So the LSTM is working well in this range and is not working well in the very low or very high formation energies. So what one could do is, if one wanted to really use an LSTM, these could be removed and you could deploy a model only in this part. So these could be treated as outliers, but then obviously your model will not be able to make any predictions that are correct outside of this range of say 600 to 1200 kilocal per mole. Right. And finally the hybrid GRU plus ANN parity plot, this is really nice, the model works beautifully, and you can see that almost it's nicely along the y equals x line. Okay. So after experimenting with various architectures, GRUs, LSTMs, RNNs, hybrid models incorporating ANN layers, the key observations are as follows. The GRU underfits, right. It is not able to, given a string representation of a nanopore in graphene, it is not able to predict at all the formation energy. It underfits terribly due to a relatively simple architecture and struggles to capture the long range dependencies that exist in the strong. So by long range dependencies, what do I mean, right. If you look at a particular string representation of a nanopore geometry, right. So there is a certain order in which these letters are appearing, right. So there is A, F, F, Z, F, F, Z, and this order determines the shape of the nanopore, right. So that is really important, and a GRU clearly is not able to capture that. Okay. Then an LSTM, it performs actually reasonably well and is able to effectively handle long term dependencies, and this is because of the memory that is there in the LSTM, which captures the longer range effects. And finally, you could achieve better performance with a hybrid GRU plus ANN, which outperforms both the plain GRU and the LSTM, as the ANN layers are able to model the complex nonlinearities after temporal or sequential features have been extracted through the GRU. Now, one thing you could try at your end, you could try an LSTM plus ANN, right. So, there are various things that you can try at your end. So, the concluding note is that the final validation MSE for the hybrid GRU plus ANN is around 80 kcal squared per mole square. This implies an RMSE of around 9 kcal per mole, and the take home message is that the hybrid architecture demonstrates the benefit of combining sequence modeling with dense nonlinear transformations, enabling superior predictive performance on complex data sets like this strong data set. Right. So, this brings me to the end of this particular tutorial. In this tutorial, we looked at basically how to implement recurrent neural networks, including LSTMs as well as GRUs for the string representation of nanopore geometry data set. So, we were able to predict the formation energy given the string representation, right. And finally, we have reached the end of the course. We have come a long way in this course. We started with things like probability and statistics, Bayesian and frequentist statistics, and then we moved on to probability distributions that are frequently encountered in machine learning. We looked at linear regression, nonlinear regression, support vector machines, decision trees, gradient boosting, bagging, so many different things, and finally we have finished today's tutorial with neural networks. Thank you for sticking out till the end of the course. I hope you learned something new in this course. Thank you very much for joining. I hope you had a great experience, and I look forward to seeing you sometime in the future. Take care.